Okay, good morning, everybody, and thank you, Yanis, for this kind introduction. Just a word, I am no longer professor, I am honorary professor now. I don't teach it anymore. So, as you know, all of you, there are many means to mitigate liquefaction on a site. Some of these techniques are well known, proven by observation during earthquake, like, for example, densification by vibrofotation or any kind of densification, dewatering, stone columns, and so on and so forth. These methods, these techniques have been validated, as I mentioned, and we have quite detailed design guidelines. Now there are other techniques which are a little bit more recent, for which we don't have such an experience and we don't have all the detailed guidelines. And this is typically the kind of technique I will present today, which is a lattice type soil improvement with deep mixing soil. I would call it DSM grid because it's shorter. Okay? So you should not be misled by the word novel approach. It's not a novel approach. It has been implemented in several projects. What is new here is the way we design this technique. Okay? So, with that, I will just briefly mention two projects using this technique, just to motivate the study. I will come back very quickly on an overview of how we can approach liquefaction assessment, and you will see this is where we have something which is new. Then we will turn our attention to the fundamentals of seismic behavior of DSM grid. And of course, to make the liquefaction assessment, we need to define the seismic capacity and the seismic demand. And with that, we will go to the design procedure. As you will see, it's based on numerical analysis and centrifuge test. Okay? So, what is the motivation? If you look at this plot here, I'm sorry, it's not very clear, but it represents the amount of soil improved with the deep mixing method along the year here. Okay, no, sorry. Pointer is here. Okay, here is the year. Here we are in 2000, and here in 2015, something like that. And you see that the cumulative cubic meters of soil treated by soil mixing amount to almost 80 millions. Okay, and it could be onshore or offshore, and the black here is the both. Okay. Now, if you look at the observation, we have very few observations, as I mentioned, and one famous one was during the Kobe earthquake, or the Yogo-Kenambu earthquake in 1995, which is the Oriental Hotel that you see here. It's a 40-story building, and the foundation of this building is quite innovative. The building is founded on piles, that you can see here, but the piles are protected by caissons made with deep soil mixing. Okay? And the result of that is that the building survived the earthquake with very few damages. Okay? The second example, and for those of you who were here, let's say in 2018, where I presented that project already, but at that time we just completed the project. It's a building in the Caribbean, in Fort-de-France, in Martinique, and the contractor was Soletange-Bachy. And the problem there was the building is constructed on a reclaimed hydraulic field, which is more than 10 meters thick, on top of a sloping rock surface. And due to the highly seismic area, characterized by the magnitude 7.5 and a PGA of 0.36 G, lateral spreading was a real issue. So, what was done at that time is to, inspired by the Kobe Oriental Hotel, we founded the building on this grid of trenches made with deep soil mixing here. And you can see here, okay, this is the site. You can see the grid here. Okay. The justification of this foundation was quite easy because we did not care about liquefaction within the cell. The building was designed to rest only on the trenches. Okay? And the only issue was to protect lateral spreading. So justification was quite easy. But of course, the contractor, Soletange-Bachy, wanted to go further in the future, and they needed some more precise guidelines, even to account for the pore pressure buildup within the cell, trying to, let's say, have a building which is with a roof which might be thinner, and so on and so forth. So that motivated a research project that was sponsored in France by the National Federation of Public Works and by Soletanche-Bachy. And these are the results of this project that I will show now. So, first of all, we have to go back to liquefaction assay. Oops, there is a mistake here. Okay, to the liquefaction assessment. And when I say we have to go back to the fundamentals, because usually people assess liquefaction based on the stresses induced in the ground. But liquefaction is a strain-governed phenomenon. And this is clearly shown here, and this is taken from a recent paper by Ricardo Dobry and Tarek Abdoun, showing that the results of undrained cyclic strain control test show practical advantages of using the shear strain, gamma, instead of what we call the cyclic stress ratio, which is the induced shear stress, normalized in some way, to characterize the pore pressure response of the sand. And if you look on the left-hand side here, you have a plot of the induced pore water pressure versus the cyclic stress ratio, versus the stress. On the right-hand side, the same tests are correlated to the induced cyclic strain. And you see here we have a clear correlation, here we don't. Okay? This is not really new, and I don't know why people did not pay enough attention to strains. Because if you look at the results here obtained by Silver and Seed back in '71, and this was obtained on a dry sand, so this is not the pore water pressure, this is a vertical strain, but if you have a saturated sand, this is exactly the same thing. And you see that whatever the density of the sand, whatever the number of cycles, it's perfectly correlated with the cyclic shear strain. And this is again the same plot in terms of pore water pressure taken from Dobry and Abdoun. So, evaluation of soil liquefaction. What we are doing right now, and when I say right now, it will even be the same in the new version of Eurocode 8, which will come out in a few years because it goes to the formal vote next year. It's a stress-based approach, like the one which is well known now, described in the NCEER report, or the one used by Idriss and Boulanger, which will be recommended in the new version of Eurocode 8. So it's a stress-based approach in which you have to define the seismic demand in terms of cyclic stress ratio, induced stress. You have to compare it to the seismic capacity, the cyclic resistance ratio, which is usually obtained from field tests like SPT, CPT, even VS. And then you calculate a factor of safety, which is a ratio of both quantities. What we propose here, we do not propose that. What was suggested by Ricardo Dobry is to use a strain-based approach. In that case, the seismic demand will be expressed not in terms of stresses, but in terms of induced cyclic shear strain. And the seismic capacity will be expressed as the cyclic shear strain that triggers liquefaction, which I call gamma CL. Okay? And this is the approach we will follow in this presentation, and this is why I say it's a novel approach, because it has not really been used until now. So, we will focus on one type of DSM technique, which is this DSM grid, which can be realized here like with second isolated column, or with more complicated shape like here, or with trenches like in Fort-de-France, the building I've shown in the presentation. And there are several patents taken by Soletanche-Bachy to realize this kind of DSM grid. Here you see the different one with the cutting, mixing, and so on. Okay? So, how does it work? at least qualitatively, you can imagine when you have a caisson, it's very stiff, it's stiffer than the soil, which means that you increase the overall stiffness of your soil profile, which means that you will decrease the induced cyclic shear strain. And from what I said, if you decrease the cyclic shear strain, you will decrease the induced pore water pressure. This is basically the idea behind this DSM grid. It's not new. Some people have already studied that, and I quoted here 2 studies, both in 2013. The first one by Nguyen and al. Was published in the ISC Geotechnical Journal. It's based on numerical analysis. The second one, by Guéguin et al., it was the topic of his PhD thesis at École Nationale des Ponts et Chaussées, and it's based on an analytical approach using the homogenization technique for composite materials. What is important to realize that both studies here assume an elastic soil behavior and a stress-based approach. We are still with a stress-based approach. What do they found? They found the same thing, which is quite comfortable, which is very important. First of all, if you look at the shear strain in the improved soil, they both concluded that the shear strain is not homogeneous. You don't have compatibility between the strain in the reinforcement and the strain in the soil. And this is very important because many guidelines, if you refer to the work by Bayes and Martin, for example, they assume homogeneity between the reinforcement, the column, and the soil, which is not the case. And this is very important. And the second finding, I took that picture from Guéguin and al. So this is an analytical solution. What is plotted here, on the horizontal axis, it is the replacement ratio, the amount of improved soil normalized by the total volume of soil. And what you have on the vertical axis is the ratio of the homogeneized ground divided by the shear modulus of the soil, by the stiffness of the soil, the virgin soil, okay? And you have different techniques here. You have this isolated column here. You have a trench, which is oriented perpendicular to the seismic loading, to the direction of motion. You have a trench, which is oriented in the direction of loading. Of course, both solutions here do not make sense in earthquake engineering because the earthquake has 2 directions, not only one. So in the middle, you have what we call this DSM grid, where we have trenches in both directions. And if you look here, for example, the isolated column, which is commonly used with the stone columns of jet grouting technique and so on, for classical, let's say, replacement ratio of the order of 20–25%, you see that you will modify the ground stiffness by no more than 20–30%. Now, if you go to this DSM grid, you may almost double and even more the stiffness of the soil. And as I mentioned, if you double the stiffness, you will decrease the strain and so on. Okay? So we started from there. And we tried just to go a little bit further. First of all, to use a strain-based approach, and second, to relax this assumption of linear elastic behavior for the soil. Okay? So we have these 2 ingredients, the seismic capacity and the seismic demand. Seismic capacity. Once again, we went back to this work by Dobry and Abdoun, which is quite recent, 2015. What did they do? They re-examined the liquefaction chart, I will call them liquefaction chart, where you plot here either any parameter, it could be VS, here it's VS, it could be the blow count in SPT test, it could be the point resistance in a CPT test, and on the vertical axis you have your cyclic resistance ratio. So they re-examined the whole database, and they focus mainly on this material here, which correspond to loose, silty, clean sand or uncompacted field, recent deposit, and so on. And what they found, which is plotted here, you have all the points here from the database. The white or the empty circle here correspond to non-liquefied soil. The black dots here are liquefiable soil. And the curve separating along this curve, which separates both sets, the shear strain is remarkably constant. It's equal to 0.03%. So we will start from that. This was done, as you can see here, only for magnitude 7.5 earthquake, simply because this is the population which is the most represented in the database. So we started from this idea, and what we did, we just redo the same calculation as Dobry and Abdun for different magnitudes, from magnitude, I can see from here, from magnitude 5.5 to 7.5, okay? So we did exactly the same, nothing new. We just re-implemented the Dobry technique. And we end up with this curve here, which can be approximated by this equation here, related the cyclic shear strain necessary to induce liquefaction as a function of magnitude. Of course, if you plot 7.5 here, you will go back to 0.03% found by Dobry and Abdun. What is important to realize, this quantity now will replace our cyclic resistance ratio. Okay? Second point is the seismic demand. So the seismic demand, were evaluated from both experiments in a centrifuge facility. These tests were run in what we call now Gustave Eiffel, as Yanis mentioned. It was formerly IFSTAR and even before LCPC. So we ran a few centrifuge tests. Then we calibrated our numerical model against this centrifuge test, using this time a 3D elastoplastic soil behavior. We use the Prevost model. So we validated our numerical model versus the test, and then we run extensive nonlinear dynamic finite element analysis with recorded time history with magnitude spanning in the range 6 to 7. Okay? So just a few pictures. I'm glad that Yanis presented the use of centrifuge. I don't have to explain why to use a centrifuge. So this is the one in Nantes, in IFSTAR. It's a little bit smaller, as you mentioned, than yours, because the capacity is 2 tons at 100 G. The radius of the centrifuge here is 5.5 meters, and you can put in the centrifuge the laminar box, exactly the same kind of laminar box to model the soil response, and the shaker, which is nothing but a shaking table that you will put in the centrifuge. Okay? So we use that centrifuge facility to run some tests. I have no time to present that, so I will just take one example to show you. Here, the test is made, you have 3 cells along that direction and 1 cell in the perpendicular direction. You have the sand. This is heavily instrumented with pore pressure gauges, with accelerometers, and so on. And I just compare, for example, for this gauge here, the computed time history of displacement. So in black, it's the analytical or the numerical model. In red, this is the experimental test. And on the right, you have the Fourier spectra of the acceleration time history at the same location. Again, in black, this is the numerical analysis, and in red, the experiment. So we were quite satisfied with that, and we could proceed now to the numerical analysis. So the numerical analysis, this is the view of model. We model only 1 cell, or even half a cell, because it's symmetric. Why only 1 cell? Because we assume that we have a significant number of periodic cells, and we can just isolate 1 cell, putting the appropriate boundary condition. So you have 1 cell here where the soil inside is modeled with a nonlinear model. The DSM trenches are modeled with an elastic material this time. So you have here the soil column here. You have the trenches here going to some depth. And we will examine 3 cross-sections near the base, mid-height, and surface. Okay? The dynamic analysis were carried out, as I mentioned, with 30 time histories, which were imposed, of course, because it's a nonlinear calculation. We have to impose it at one outcrop of the base of the soil column. Okay? So just to give you a brief idea of the constitutive model, I'm sure that some of you know them. Prévost's model, I like it very much because I have been using it for more than 40 years. So you see here, this model is a nonlinear elastoplastic. So you have linear elasticity in which the shear modulus and the volumetric modulus are expressed as a function of the effective strain. And you have plastic parameters. You have, of course, the friction angle. We put a small cohesion for numerical problems. And then you have the definition of the nonlinear stress-strain curve through the G over G max curve and the dilation angle that will model the volumetric strain. Okay? What are the parameters which are involved in this analysis? You have parameters related to the sand itself, so the shear modulus, mass density, height of the soil column. Oops, sorry. No, I'm going the wrong way. Sorry. When I mean height of the soil column, this is the height from the ground surface down to the soil, to the base of the model. Okay? So you have the height of the soil column. You have, of course, what will be important is the maximum free field cyclic shear strength, the one you will get without the soil reinforcement. The trenches are characterized by their shear modulus, mass density, height of treatment, which is different from the height of the soil column, and also the trench thickness, the spacing between trenches, B here, the trench thickness, and of course, the average shear strength induced within the cell. That would be a result of the calculation. And then the ground motion is characterized by its magnitude and PGA. PGA, I use the ground surface acceleration, which is a result of the calculation because we impose the motion at the base. We scale the motion at the base between 0.05 g up to 0.45 g. Okay? So you see that we have here 11 parameters. Hopefully, we made some dimensional analysis, and we know the Vachy-Buckingham theorem. In France, we call it Vachy. In UK, they call it Buckingham. Okay. So we have 11 parameters, 3 fundamental quantity. No, sorry, it's not the right. Here, I'm just showing the way we just modify the different quantity. We parameterize the shear modulus of the soil, the shear modulus of the trenches, the height of the treatment, the spacing between trenches, also the thickness of the trenches, and the earthquake. Okay? So we had, as I mentioned, 11 parameters, 3 fundamental quantities, which means that we have 8 independent dimensionless quantities, which are listed here. Some of them are obvious, like the ratio between the trenches and the soil, the replacement ratio, the aspect ratio, which is the ratio, the width of one column divided by its height, and so on and so forth. Okay? So we run our analysis, more than 100 analyses, and we just try to use the results in terms of this dimensionless parameter. I will just show you 2 examples here. This is one analysis where you have plotted versus depth. This is the depth of the caisson. For 3 locations, 3A and B, you have the maximum induced shear strength within the cell. Okay? What is important you see here is that from the surface to, let's say, 90% of the height of the caisson, it's almost very smoothly linear, which means that we were able to take the result at the surface at mid-height and to extrapolate linearly down to that depth. What is very important here is to see that the shear strain is increasing very much close to the bottom of the trench. Okay? And in that region, the induced shear strength represents maybe 20 to 60% of the free field shear strength. Here, it could be higher by 20 to 50% than the free field shear strength. And this has very important implications for design. And as you can see here, this is a cross-section within the cell at mid-depth with the maximum shear strength recorded here. As you see, it's not homogeneous. So we have to average that shear strength here You see that here it's higher, close to this trench here, because you have bending flexure of the trench, so that will increase the shear strength. And it's very small here, or it's smaller here, because you are close to this wall, which is acting in the direction of loading. Okay? So what we did, we tried to relate the free field shear strain that we assume we can get from another approach, site response analysis or anything else, and we tried to relate that cyclic shear strain in the free field to the average cyclic shear strain within the cell. So what you see here are all our dimensionless parameters. You see modulus ratio, the replacement ratio, and so on and so forth. And we fitted that to that equation where you have parameters, theta 1 to theta 7 here, which were just fitted to the results. And just to show you the results here, you have a plot where the calculated average shear strength coming directly from the numerical analysis is compared to the predicted one from the previous equation. And you see, okay, here this is close to the bottom of the column. This is in the middle or top of the column. Okay? So you see that we have quite a good agreement, and we are quite satisfied, and we are able to use it. And go to this design flowchart here, where you have the input data, the seismic data, magnitude that will give you the liquefaction, the shear strength triggering liquefaction. Then you have the DSM data, the spacing, height, modulus, and so on. You have the geotechnical data, the soil characteristics. And of course, you need the free field shear strength, so the free field site response. You can get it from a site response analysis or with more simplified approaches using, for example, the NCER approach. Okay? So with all these input data, we can calculate the average induced shear strength within the cell, which is a function of my dimensionless parameter, and compare it to the shear strength triggering liquefaction that we get from the seismic capacity we derived. And then we compare, okay, if it's less than gamma CL, everybody is happy. If you are happy, what you can do, you can compute the induced pore water pressure using any kind of pore water pressure model. Okay? If not, of course, you have to redo your design or use more refined analysis. So this is the design flowchart that now Soletange Bashi is using for preliminary design. So just to conclude, DSM grid, they offer promising perspective because they are less expensive than any other kind of soil improvement. They are quite quick to implement. From the environmental point of view, it's better than jet grouting, for example. And also, it might be cost efficient because if you can found your building with a shallow foundation, it's less expensive than with a pile foundation. So based on extensive numerical 3D analysis, which we have validated by comparison with centrifuge, we defined this design procedure. And what is novel here is the fact that it's a strain-based approach, which I consider more fundamental than the stress-based approach. Of course, you cannot evaluate your safety with a factor of safety. What you have to calculate is the induced pore water pressure and see if it's acceptable or not in terms of post-earthquake settlement. Just a warning here, because I saw some people trying to use this design flowchart for situations for which they were not developed. For example, in a sloping ground, like we had in Monaco, for example, for a recent project, we have a sloping ground, and these results should not be used. But it does not mean that the philosophy of the guidelines cannot be used. You simply have to calculate your induced cyclic shear strength differently, and then you can compare it with your seismic capacity. So with that, I will conclude, and thank you for your attention.
Thank you very much for a great presentation, Alan. We have time for questions, actually. So if there are questions or discussion, yes, I see Sasa is raising her hand.
Somebody else? I can wait.
I didn't see any hand yet. Ah, there is one hand back there. Okay. Adonia, maybe we start with where you are closer.
You said that you used linear stiffness for the soil mix material. How much is the impact if you use a non-linear material? Because the cutter soil mixing, of course, is very unpredictable. What is the result of
Yeah, you are right. I don't know. I cannot answer your question. I don't know. But what I know is that you can increase the strength characteristic just by adding some cement and so on. For example, in the example we had here, the unconfined compressive strength was varying, which was related to the shear modulus, was varying between 3 and 5 megapascal. But we can go up if we need. But you are right, we did not, that could be the next step to implement a nonlinear model for the DSM trenches.
Sasa?
Thank you very much, Alan. This was really interesting talk. And I agree fully with you. Strain is more fundamental than stress. Yeah, stress is a concept. Strain is something that you can measure. So I like it a lot. But my question is, you know, everybody got used to NCER. This is something that is universally accepted. What happens if someone now comes and develops a similar approach as a stress-related approach? Are you not worried that everybody is going to use that one and not yours?
You mean if somebody is making the same approach but on a stress-based approach?
Yeah.
This is exactly what Nguyen did in their paper in 2013. He did numerical analysis and he just modified the cyclic stress ratio to account for the stiffness of the DSM grid.
Okay. And
But
so, nobody's using his approach. They're using yours.
I don't know. I am using mine, but I cannot.
Because it's I guess it is now important to go back to NCER and to change that to strain base.
Yeah, this is what Dobry and Abdudin did. As a matter of fact, they use the charts which are in NCER and they just reinterpret it in terms of cyclic strain.
But is it like getting used broadly or only by Dobry?
It's only by Dobry. You know that Ricardo has always been a fan of the cyclic strain. And
Right. Yeah. Can we go quickly back to slide 15?
Yeah.
For my second question.
Oh, sorry. 15.
Yeah, we're almost there. Yeah, here.
This one, yeah.
Your approximation, it is related to the solid line, right? To the solid red
exactly.
line.
To the solid line and the two dotted line as a range of values you get because when you inspect the database, you have different confining pressure, different at-rest earth pressure ratio, and so on.
Okay, so this was my question. Where does the scatter come from?
Yeah, and the scatter also comes from the magnitude correction we used also. There is one which is proposed in the NCER, but there are several others. So we use also different magnitude correction factors. So the scatter is coming from that.
But then, you know, I mean, the scatter is not small. We have an order of magnitude.
No, it's,
right?
I agree. Yeah.
How would that affect my analysis if I go for an average line?
Yeah, that I don't know. You have to make the analysis, but you can use, if you want to be more conservative, you can use this one, or if you want to be less conservative, you can use that one.
Okay,
but,
thank you.
But be careful. This is valid only for, as I mentioned, loose recent sand deposit or uncompacted field. If you go back to, I don't know where is Rick. No, okay, sorry. Here, for example, we are in that region here. We are not talking about this, okay? Here, the cyclic shear strain triggering liquefaction is a little bit higher.
Do we have other questions? It could be for, not only for Professor Pecker, for any of the speakers.
It would be better for us.
I have a question.
Yeah.
You showed in slide 25, and also in the slide you showed previously,
25.
that, yeah, here,
Okay.
okay.
25, yeah. No. Oh, no, I'm going
No, the
wrong.
other way.
Yeah.
So here, so we have some big values at the bottom.
Yeah.
So my question is, and you have this limit of 0.03, right?
Yeah.
Or in
This is, yeah.
So you would, let's say, base your design on avoiding exceeding this limit there exactly at the bottom.
Yeah.
Which you have this
and
peak.
below also, below the caisson. This
and
is something
below, yes.
you have to pay attention because you will make your grid and stop in a, let's say, non-liquefiable layer. It will be non-liquefiable in the free field, but once you put the caisson, it might become liquefiable because you will increase the shear strength. And physically, you can understand because you have a big rigid mass and the layer just below just act like, let's say, an isolation system. And you will concentrate the strain in that layer.
Yeah, but this would be exactly my question.
Yeah.
Is this bad?
Yes, it's bad. You have to pay attention to that, which means that you have to check afterwards with strains which are different from your free field, that the layer is not liquefiable.
I mean, you have this caisson which is not
Yeah.
liquefied, and underneath maybe you have a layer that liquefies.
Yeah, but in that case, you may either deepen your caisson or do something.
Okay.
But my message here is pay attention to the layer just below. This is important.
One question there. Yeah.
It's just in line with your question, because if we go down further, we increase the mass. So we may end up in the same situation because, we have to go down to the rock bed. Yeah.
No, because okay, soil is not really homogeneous. You may find a layer which is much denser and
Yeah.
no, but for example, we have implemented that in France in the 2 projects and also in Monaco, where we found a layer which is a little bit denser, and we checked that it was non-liquefiable below. If you have rock, it's even better, of course. For example, in Fort-de-France, the caisson went down to the rock. Yeah. Yes?
But if I may also continue on that issue, how thick would then be the layer which is where it is possible to liquefy below the caisson? If it is maybe thin, then it's not so important. But if it's get thicker,
It could.
do you have results from your numerical assessment? You don't show what happened below.
Yeah, I have results, but I don't have them with me here. But of course, we have the results down to the bottom of the soil column. Yeah, but it's not so thin. It could be, let's say, 1, 2, 3 meters. It's not 20 centimeters, no. But you are right. Maybe it's not a great deal because, for example, if it will create vertical settlement, maybe. If it's a thin layer, we don't care. And since it's deeper, if you don't have a sloping ground or if you don't have lateral spreading and so on, okay. Nobody cares. For the structure above. Because the structure will rest on the trenches, and the trenches will settle almost uniformly. That was the philosophy in Fort-de-France.
This is what I meant. Actually.
Okay. Okay. Thank you.
Do we have other questions? Okay, maybe ask one more question.
Yeah.
Since taking advantage of my role. Based on your analysis, what is better to have, let's say, these trenches, more of them, let's say, denser grid, or thicker trenches?
From my experience, the good ratio is, let's say, thickness in the range of 0.8 meters and spacing not larger than 6 meters. Okay. Because if you go further, then it doesn't work really.
But
because the replacement ratio will be smaller and so on. So
no, let's say we have the same replacement ratio.
Okay. In that case, it's better to have closer trenches which are a little bit thinner.
Closer and thinner.
Yeah.
Okay. Okay.
But not thinner than 0.6 meter, because after you have some construction issues and so on. Because I did not talk about that, but you have to check that your trench is continuous and so on.
And I'm also interested that there is this magic number of 003.
Yeah.
Do we have an explanation?
I don't know. No, it just. But it's quite. This is a
Yes.
threshold. You know, for example, if you go back to. No, not that one. Okay, you know, you have this cycle. Oh, sorry, no, it's here. Huh? Pointer. Okay, you know that Dobry defined this threshold for cyclic, for volumetric strain or so on. So triggering is a little bit higher, but it's a threshold. And how it comes, this is the work of Dobry. He just re-examined the database and found that.
So if it's for any type of soil, let's say?
No, for loose sand deposit, recent deposit, and so on. No.
Okay, but for any type of sand, let's
Yeah.
say. Okay.
For liquefiables.
Yeah.
Those who are present,
Liquefiable, but there are many types of sand, yes.
I would say the sand which are present in the database.
Okay. Okay, do we have other questions? Okay, if not,